All right. I will begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for the students. Just ask you to bless our work today, help us to glorify you what we do, and just understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. Do you guys have any questions before I get started? Okay. So I think last time I said something about more examples of rotational kinetic energy and so forth, and I think that's a misnomer. I don't have any more examples. We should go on to torque. That's like the next thing. So I did warn you I wasn't thinking clearly last time. So anyway, here we go. So we're in my section 7.5, which is on angular momentum and torque. So we'll talk about that. So let us begin with the definition of angular momentum here for a mass m. Mass m with velocity v has angular momentum L, use capital L, it's a vector, and it's equal to the cross product of R with momentum, or if you prefer, R cross mass times velocity, or of course, we could write this as mass times R cross the velocity. All right. So this is the angular momentum of M. All right. Let's see here. So we could try to, I guess we could try to picture this if we wanted, right? Like what would this look like? So we can get this marker to work. So it's obviously a three-dimensional thing, right? So if we imagine the the trajectory of some particle, maybe it's like this, right? Then relative to the origin, we have R here, right? And I'll draw it over here as well. In two different instances. And the velocity points in the direction of the motion, right? So like something like this, yeah? Which of course is the same as the direction of the momentum, right? The momentum and the velocity are collinear. So what would the angular momentum look like? Something like we do R crossed into V, right? So the angular momentum here would be something like into the board like that. So I think my picture is something like this. And then over here, R crossed into V. I guess it's into the board, something like that. So maybe it's more helpful for me to do a picture that's a little bit easier to understand, something really boring. Like, suppose we've got circular motion, all right? So I'll do it up here, maybe. All right, circular motion. And we'll make it go this way, all right? And all right, so my radial vector, something like this here. The radial vector would be like that over there, right? And my velocity, let's see here. So the velocity at this point is going into the board, right? So the velocity vector would be something like this here. And over here, velocity vector would be coming out at you. Where's the angular momentum? We do R crossed into v. Man. R crossed into v. It looks like I've got. Sorry, I'll get it eventually. R crossed. Oh, it's into the board. R crossed into v. So it's like this, right? The angular momentum. How does it relate geometrically to the R and the v? It should be perpendicular, right? This is what the cross product does. It gives us a vector which is perpendicular to both of the vectors being crossed, right? So the angular momentum should be perpendicular both to the radial vector from the origin as well as the velocity vector. So that if I did this picture right, this right here would be like a right angle between the R and the L, right? Over here, R, now it's come out at you, right? Crossed into V, so it goes like this. So this would look something like this, right? Now, if it was constant velocity circular motion, then my L on both sides should have equal magnitude in sort of opposite, well, not exactly opposite direction, right? But what direction does the angular momentum point towards? It's like the axis of the rotation, right? Now, if we put the circle in the plane of motion, even a little bit prettier still, all right? So let me put the circle in the plane of motion this time. All right. Then that was supposed to be a circle. My radial vector here would just be like this, right? And my velocity vector, assuming it's still going the same loop-de-loop way as the last one, right? So the velocity vector there is going into the board, right? And R crossed V is what? Just straight up there, right? Straight up. So L would look like this. All right. And if I did the I'll do it over here, I suppose. This one, right? And then my velocity is going out of the board, out at us here like that, right? Then what? R crossed into the velocity, right-hand rule, directly upward, right? So I hope this helps you guys gain some appreciation for the directionality of the angular momentum as it relates to the velocity and the position, right? It depends. Like the angular velocity, it's going to like its value, its direction, totally depends on what we choose for the origin, right? If we shift the origin to somewhere else, it completely changes the angular velocity, right? Angular velocity definitely depends on our choice of origin. Yeah. But we see that if we have circular motion, right? If you have circular motion and it's in like a plane, then the angular velocity should point, according to the right-hand rule, in the axis, along the axis of the rotation, right? So here we're going in this circle. My right-hand rule, if I grip the circle and kind of wrap my fingers around it, my right-hand thumb is pointing in the direction of L. And that L is constant. So L indicates the axis of, sort of the natural axis of motion for circular motion. All right? All right, so next up, let us calculate what happens if we differentiate the angular momentum. So what happens if we calculate dl dt? What's that work out to? So we've got d dt of, let us say, I'm going to do r cross p, so because I like that one. And there is a product rule for the cross product. The product rule for the cross product is simply this. It's dr dt cross p plus r cross dp dt, right? Or let's write this out a little bit more. So what we're looking at here is, I'll pull the mass out. We've got mass, the velocity cross the velocity, plus r cross dp dt. So you guys tell me what happens here. What's v cross v? You guys remember? We did do cross product earlier this semester, did we not? Yeah, we did. What was one of the fundamental properties of the cross product? It is any vector cross itself is 0, right? So v cross v is 0. So this right here is no more. And how about dp dt? What's this? If we're talking about, well, if we wanted to relate that to a force, what force would that be on the mass? What is dp dt? How about the net force, right? So remember, the net force is equal to m times dv dt, but for a mass, that's also equal to ddt of mv, which is, of course, dp dt. So this was the momentum form of Newton's second law, right? The net force is dp dt. Momentum is a vector. Force is a vector. Now angular momentum is a vector. And the time rate change of angular momentum also, you guessed it, a vector. So, what we got? Well, here's the next definition. Torque produced by F with respect to a radial vector R is torque is equal to R cross F. So this is the torque produced by a force, R cross F. And what this means then, so we have basically a theorem that says that dl dt is equal to R cross the net force, right? But we can justifiably call that the net torque. It's the torque produced by the net force. What is this we're looking at here with this theorem I've just written down? Oh, I almost forgot. If you could add an exciting new day to this. All right. So what I've just boxed up here, this is the rotational analog of Newton's second law, right? This is Newton's second law. So before we immerse ourselves in the one-dimensional examples again, let me take a second here to do a genuinely vector problem. I think it's a good chance for us to practice our cross products a little bit. So let us work out how this works in the case of like projectile motion. All right. So here we go. So example 1. What is the formula for projectile motion? So suppose we're at r naught at time 0 with velocity v naught under net force minus mg z hat, right? So this is the force of gravity close to the surface of the Earth. All right. So first of all, we can integrate. We know what this means, right? This means that This is, of course, equal to m times the acceleration. So we get that the acceleration is 0, 0 minus g, or if you like, minus gz hat, yeah? So we have this constant acceleration due to gravity. If we integrate this, yeah, so this is equal to dv dt. And so we integrate once, we get the velocity is equal to the initial velocity minus gtz hat. All right, so there you go. That's my formula for velocity. And what's the formula for position? Well, I integrate again. Right? And then integrate again. And we get the position is the initial position plus the initial velocity times time minus 1/2 gt squared z hat. All right? So now what we can do is we can calculate the angular momentum, right? Let's go ahead and calculate the angular momentum for this. So find angular momentum. So we know L is equal to m r cross v, right? mr cross v, that's the angular momentum here. And I'm doing it with respect to the origin. So I've got m, and that's going to give me r naught plus v naught t minus 1/2 gt squared z hat. And I'm supposed to take the cross product of that with v naught minus gt z hat. All right. So what I get from that is a little bit symbolic, but I get m r naught cross v naught. I mean, I can't really simplify that more than that. And then I get minus gt r naught cross z hat. So at the moment, I have just taken the first term and taken the cross product with these guys. All right, that's these terms. Next up, I have v naught t crossed with, so you guys tell me what happens when I take the cross product of this piece here with this piece here. What happens? That piece is 0, so that's good. But we do get a minus gt v naught vector cross z hat, all right, from the remaining term. And then I get minus 1/2 gt squared z hat vector cross v naught, right? And that's it, because the remaining term, the z hat cross z hat term, is also 0, because again the cross product of the vector with itself is 0. All right. Can we simplify this at all? Did I miss a t squared? Oh, in the first. Oh, this one? Yeah, that should be a squared. Thank you. Let's see here. I think it might be useful for me to just go. Okay, so that's r naught cross v naught, right? And then I've got looks like minus. Well, fine. I'm trying to decide how to write this. Plus, I'm going to use a plus. 1/2 gt squared v naught minus gt r naught minus gt squared v naught all cross z hat. So what I did there I wanted to factor out a z hat because I can. But you notice here on the last term, I had to flip the order of the v naught and the z hat, so that's why I got a plus on that first term, right? Now, this is nice for when I do the next step, which is to differentiate L. So like this is just a formula. This is apparently what the, and I guess we could simplify it further. Oh, we could simplify this further, couldn't we? Do you guys see how this simplifies? Notice that this term and this term, they go together, don't they? So what we got? Plus, apparently minus 1/2 gt squared v naught minus gt r naught, all across z hat. All right. Put some big parentheses around this whole thing. Now notice that the initial term here is just a constant, right? This is just a constant. So when we differentiate, that differentiates to 0. What's dl dt then? So this differentiates to 0, and I get this differentiates to what? Minus mg minus mgt v naught. This differentiates to minus, I'm multiplying the m through apparently, minus mg r naught. I think that's it. Now all of this was crossed with what? Z hat, but z hat has no time dependence. So if I calculate the derivative of this quantity, I can just differentiate this business right here and take the cross product with z hat. That's the derivative, all right? Notice that this can be rewritten as r naught plus t v naught crossed with minus mg z hat, which, by the way, is r cross the net force. Which is what we said had to happen. So I've just shown you that for this specific example, if we calculate the angular momentum, right, as a vector, and we differentiate it, then we will in fact get the net torque, which in this case is, you know, r cross minus mg z hat. That's the net force here.
So where did the negative 1/2 gt squared z hat go? Like if you were saying that r naught plus t v naught.
Where did this go? So what I did was I took this right here, and it is exactly this right here under ddt.
From like that, your second class that where you cross and then you become r cross infinite. Like that r doesn't match the r above.
So I flipped them. So this one came first, and that one came second. Notice that I kept the t and the v naught, but on both of these I had a mg, right? This minus mg is here and it's here, so I factored it out to there. Oh, that's not my r?
Yeah, that's what. Yeah.
Oh, yeah. So there's one more step. Thank you, I gotcha. So can somebody tell me why this next step is okay? So you're like, I'm missing this, right? And you're absolutely right, I was missing that. And yet what I wrote down was not incorrect. This is really kind of a pernicious step, but The reason for that is I've added 0. Because z hat cross z hat is 0. So, yeah, I know, right? So this is, like I was writing a second ago, this is indeed r cross the net force. Okay, so anyway, angular momentum is a 3-dimensional quantity in the abstract, and we have to deal with it as such, right? We have to calculate cross products and all this business, right? This is what it looks like 3-dimensionally. It is this. And we can also define, angular momentum in this sense. Another formula I should mention, probably, going back to my initial definition, is we can also define angular velocity as a vector. And angular velocity as a vector, here's the rest of that story. It's not much. It's just that this business right here, it's also equal to, oh, no. I'm sorry, guys. Hold on a second. Let me not say it wrong. Moment of doubt. Yeah, omega is r cross v. So this is also equal to m omega vector. So the angular velocity vector is r cross v. All right. Let me get the projector out here. Maybe I guess I don't need to. I'm about out of dark colored markers, so it's kind of, if you guys can you guys see the red? Okay, good. Sometimes it's not working, but did I move the I can't remember if I moved the camera back or not. All right, guys, so here's the thing. The full story of angular momentum and the moment of inertia, it does take us a little bit beyond the course. All right, so let me see if I can explain without getting too far into the weeds here. Let's see here. So basically, here's the thing. The torque, all right, as we've talked about, is dl dt, right? So if we want to think about this for a small time, we can think about it. It's the change in angular momentum over the change in time, right? So if we think about this, this says that the change in angular momentum is something like the torque times a little change in time, right? So the picture I just erased foolishly showed us that for circular motion, right? For circular motion, where's the angular momentum? It's radial. I mean, not radial. It's along the axis of rotation, right? So if we think about this, right? This will be if the motion's like this, this is the angular velocity vector. It's grip the rotation of motion. Your right hand wraps around the rotation axis, and your thumb points in the positive direction with respect to the rotation axis for a counterclockwise rotation about that axis, right? So with respect to such an axis, we can define, we can pick a particular direction, and then we can study, like, or my bad, I usually put it over here. We can we can define a particular, well, we could think about this as like x and y, for example. And, of course, we can sweep out this far, and we can say, well, that corresponds to theta, and in that context, we have that S is equal to r theta, and ds dt is what? R d theta dt, right? And d squared s dt squared is what? It's r d squared theta dt squared, right? In other words, we get back to all these wonderful circular formulas. From arc length, the basic arc length formula s equals to r theta, to the, what's this one? You know, the velocity is r omega. Here we have the tangential acceleration, right, is r alpha, right? These are things we know for circular motion. Yeah? And so if we want to talk about circular motion, if we want to talk about torque with respect to circular motion, we're going to have a problem, right? If the angular momentum, the change in the angular momentum is off the axis of rotation, we're going to have a problem, aren't we? So like think about this. This is parallel to the angular momentum, right? Because if I wrote down a formula here, that feels wrong. That feels wrong. I'm going to put some quotes on this. I have a sneaking suspicion I'm missing something here. It's in my notes, but I don't believe it. Anyway, let's forge ahead here. The larger point, though, is of course that if the if the torque, right, if the torque is not in the direction of the axis of rotation, what happens to the motion? Does it stay in a circle? Think about it. What's going to happen if the torque, you know, starts going this way or that way? It's going to end up making the motion like not be in a circle anymore. It's going to take it out of that plane of motion. All right. So what this means is for us to maintain circular motion, we need a torque which is also aligned in the same way, right? Like, it's important that this torque is collinear with the angular momentum. All right, and so this doesn't have to be the case in the abstract. Like in general, if we apply some torque over some time interval, we have this relation, right? L2 is equal to L1 plus the integral over the torque. Right, this is just what we get from integrating Newton's second law rotationally. This is generally the case, you know. But if we have that the angular momentum is equal to I times omega, and if that's the case, if the angular momentum is actually equal to I times omega, if that's going to be the case, omega is constant. Oh, I'm sorry, guys. My brain's not working. So I say we should look at this L equals I omega, and the torque, of course, is equal to dl dt. That's a general truth. Let's see here. Whew. All right. So there's no if here, actually. This is like, by the way, theorem. L is equal to I omega, and the torque is dl dt, where I is the inertia tensor. I knew there was a snake waiting in the grass to get me here. Yes, sir.
Or when you put implication, shouldn't it be omega equals 0? I mean, just based have the differentiation for s equals r theta?
Omega equals to v. Well, the thing is, I don't know what r to divide by. Yeah. Maybe it should be. Maybe we could say this. Maybe we could say v is like r cross omega implicitly defines omega, something like that. Let me think about that for a second here. I need some colors. I know it's dimensionally inconsistent, like at the moment, because I've got radius times, well, maybe it's not. No, it is. Like I can't have radius and velocity both have units of like meters and velocity meters per second, right? So when I multiply those, I got like meters squared over, I know that's wrong. This might be okay because I've got at least like, I've got a meters, I've got a 1/2. This is at least dimensionally consistent. I'm worried about the order of things. I'm over here to pick a red marker. So if you look here, the velocity would be like here for this one, right? Horizontal. And the radial vector is like this, yeah? So let's test my formula, r cross omega. R, right? Coming out at us, crossed omega. Oops. So it looks like I should have omega cross r here, perhaps. If I have, unless I've talked myself into a omega crossed in r. Yeah, I think, looks to me like this should be what I write, right? So. All right, anyway, so what I'm trying to get to here is the inertia tensor, which you can define as follows. Ij is equal to the integral over Kronecker delta ij, the length of the position vector r squared minus xi times xj times the density at r dv, all right? This gives us a 3x3 symmetric tensor, matrix if you like. And this is what has to play the role of rotational mass for a general three-dimensional motion. Like we can't just, you can't just describe three-dimensional rotational motion with just one constant, because there can be different, you know, if you have a shape, it may have one moment of inertia with respect to one sense of rotation, but an entirely different one with respect to another, all right? For example, just to make this a little bit less esoteric, and again, this is the part that's a little bit beyond our course, but I think it's kind of important for us to understand the limitations of our method, which is what I'm trying to get at here at the moment. So if I had this disk, right? What's the moment of inertia of that? If we're going to think about the origin being at its center of mass, right? There are kind of two different ways to go here. The one is like a vertical axis, right? If we let that be our omega 1, let's say, that's one sense of rotation, right? We know the moment of inertia in that sense would be what? 1/2 mr squared, right? If this distance is r and this has mass m. So that's one natural choice of axes, right? But what would the moment of inertia be if I put an axis that cut through like this quarter, let's say, along the plane of the thing? It wouldn't be 1/2 mr squared anymore, would it? I'm not sure I know what it is. Can you guys tell me? I don't know. Like, suppose I put the axis like this, right? I'm imagining flipping it end over end. What's the moment of inertia for this kind of rotation? You know? I'll make it over here. We could call that the second axis, omega 2. That would be a different moment of inertia, right? I'm not sure what it is. Do you guys know what it is? Did we calculate the moment of inertia of a circle I don't think we did. Like, this would actually be, that would actually kind of be a pain, wouldn't it? To calculate that moment of inertia, wouldn't it? What would we have to calculate? I mean, I could set it up, but let us agree that that would be something different than 1/2 mr squared. I think that's clear, right? So how do you describe rotational motion for three-dimensional objects? Because you can't do it with respect to just one moment of inertia, right? There are different axes which have different, I mean, pretty much any axis you pick through the center of mass, you're going to get a different moment of inertia, aren't you? So what this thing does is it says, okay, fine, we'll just calculate this matrix, which basically covers all contingent possibilities, and it shows you how a solid object rotates around any old axis, all right? We don't do matrices in here, so it's beyond us, right? Also, we don't want to do that integral, all right? But the beautiful thing, guys, is that this is actually a symmetric matrix, which means the real spectral theorem applies, and there's an orthonormal eigenbasis, which is to say that there is a symmetry axis, if you will, to the solid. And so if we do rotation around the symmetry axis, that's encapsulated by this formula right here, that the angular momentum and the inertia tensor are related in this way. So getting to the point eventually, what I'm trying to tell you is if we study circular motion, the angular momentum is simply the moment of inertia times omega, all right? And we could add vectors here because I'm saying that the angular momentum and the angular velocity, they're aligned, they're parallel. In general, the angular momentum and the angular velocity don't have to be aligned. Excuse me, my bad. I think it's a tautology that the angular momentum and the angular velocity are aligned. That's essentially contained in this thing up here, right? But man, that doesn't feel right either. There's probably supposed to be an R there, right? I'm very. Let me review the tapes, guys. I'll get back to you on. There's something wrong with these equations here. Like that doesn't make sense to me dimensionally. Because I should have, like this right here. Like this can't be right, right? This has got mass. This has got meters. This has got kilogram meters per second. This has just got kilograms times radians per second. This equation's garbage. That is not true dimensionally. My apologies. I'm a victim of my own notes. What can I tell you? All right, so what I'm trying to get at here is if the torque is, as long as the torque is aligned with the angular momentum, we can keep rotating around a symmetry axis and we can have essentially one-dimensional motion with respect to that axis of rotation. If the torque does not align with the angular momentum, though, then we get weird stuff like precession, like the gyroscope. If you read your book, there's a whole section on the gyroscope and the precession of the gyroscope. That's what happens when the torque does not align with the angular momentum. Things get more complicated, and I don't talk about those in here except to talk about them, to not talk about them. So now if you take Dr. Budara's course, I think he actually spends like a couple lectures on precession, all right? And he makes you calculate it, which is why he's a better physics professor than I am for sure. But anyway, I digress. So, so what I'm trying to get at here, eventually, slowly, is simply that if the torque is in the direction of the axis of the rotation, then we will continue rotating about that axis, and essentially it gives us a reason for the angular accelerations that we studied the kinematics of before earlier, right? So like, for example, if I had, I'll just keep it real simple here, but if I have a pulley, all right, radius r, and the moment of inertia is, 1/2 mr squared, right? And I hang a rope over that, and the rope is essentially massless, all right? And then I let that mass drop. What happens is it turns the pulley, right? But the pulley's not massless anymore. The pulley has a mass m, right? The pulley has a mass m, and if we hang a rope off of it, and again, that rope is, like this, all right? And let's suppose that there's a mass little m here, and it's pulling down the pulley, right? So what's the torque then? The torque comes from the force that's applied right here, right? So the force is equal to little mg in terms of its magnitude, right? And so the torque on the pulley is equal to little mg times r. Well, now why is it just little mg times r? It's little mg times r because the string pulls tangentially on the pulley, right? So it's applied perpendicular to the radius arm, which would be here, all right? So like, we're talking about this being the axis. So here's my like radial arm, little r cross this f. What happens? R cross f, the rotation is, axis is into the board, okay? So like r cross the force of gravity is into the board. And that makes sense, right? Because if you take your right hand and you think about what kind of rotation is it going to produce? This kind, right? The rotation is going to be this sort, right? That's the direction of the rotation. What is the angular acceleration in such a situation? Well, we know the torque. The torque is mgr, right? And torque is also equal to I alpha, right? So this is equal to the moment of inertia for the pulley times alpha, I alpha, right? But here we've got little mgr is equal to 1/2 big M r squared. That's my moment of inertia, assuming that this is a cylinder times alpha. And so my angular acceleration apparently is, what we got here? mg big R divided by 1/2 big M r squared. So there you go. That would, we could simplify that, of course. That would be the angular acceleration. What's the actual acceleration, though, of this system? Remember, acceleration is what? R times alpha in this case. We're assuming that the string is not stretching, right? So R times alpha gives me the tangential acceleration, which is the acceleration in this context. And that is, of course, going to give me mg over big M over 2, right? Because the r's, they'd be canceling. So for example, if the masses are equal, what happens? Oh, that's weird. Is that right? That can't be right. Surely I have made an algebra mistake here, right?
Still have another R on the bottom.
I should, well, I'm getting 2G. That feels very wrong. Does that feel wrong? It should feel wrong to you guys. It feels wrong to me. I am pretty sure it should be G over 2. It should be slower if it's not free falling. If it's having to spin up the pulley, it shouldn't be free falling. It shouldn't be double free falling, right? There's a mistake here. And with that, we'll end class. That's a cliffhanger. That's a cliffhanger. That's what that is.